Hello and welcome to another session in physics. In this session we'll be looking at the topic elasticity. But before that, let us review the previous lesson. Welcome back. At this point, let's look at the definition of elasticity. Of course, you know what the word elastic means. When we say a body is elastic, already we've talked about the elastic nature of liquids, which is known as surface tension. So elasticity simply refers to the tendency of a material to regain its original size or shape after it has been deformed or after it has been compressed or extended. Take a look at the picture here and look at somebody trying to stretch a rubber band. You will agree with me that if you stretch a rubber band so much and for so long, the rubber band becomes deformed due to that extension that was exerted on it. It becomes deformed in the sense that its original size changes. Probably it becomes longer than it originally was. That is what we call elasticity. There are some bodies too that can stretch. For example, you get a piece of clothing and then you extend it or draw it. You could end up tearing it, and in that situation we say that piece of clothing has been deformed. Robert Hooke was one man who made postulations in the field of elasticity, and one of the postulations he made is the one we know today as Hooke's law. Now, according to that law, he stated that provided the elastic limit is not exceeded, provided the elastic limit of a body is not exceeded, the extension in an elastic material, say wire, is proportional to the force that has been applied. We'll look at what we mean when we say elastic limits in the following slides to come. But just get this law drummed into your head, that provided elastic limit of a material is not exceeded, the extension, how long it was drawn in that elastic material, is proportional, reacts directly with the force that was applied. So what it simply means is that force is directly proportional to the extension. So the amount of force you apply on a material, an elastic material, is directly proportional to the extension that that material will experience. So the greater the force, the greater the extension. The smaller the force, the smaller the extension. So adding our constant of proportionality, we're going to have Ke, where K is our force constant, stiffness or elastic constant. Now, what do we mean when we talk about force constant? Force constant simply refers to the amount of force that causes a body to extend. It is the amount of force that causes a unit extension. In other words, we say it is the ratio of force to the extension of an elastic material. Remember, we said force is directly proportional to the extension, so F is equal to Ke. Now, the force constant, making it the subject of the formula, you see that E will cancel itself, and then we have K equal to F over E. The ratio of the force to the extension gives us the force constant. Ratio of force to the extension gives us the force constant of that particular material. Now, if there is an extension in a material, Hooke's law is applicable up to the elastic limit. But if there is an extension beyond the elastic limit, Hooke's law does not apply anymore, because at that point in time, the material will have been deformed since it has been stretched permanently. What do we mean when we talk about yield point? Before we talk about yield point, take a look at this diagram here. This is a spring suspended on a pivot. Now, you would notice that at this point, this spring has been compressed. It is compressed at this point. From here to here, it has been compressed. Compression occurred here. But look at it here, it has been extended a little. And this extension, at least to a reasonable extent, looks normal. There is a limit at which this spring will be extended, and when you withdraw or remove your hand, the spring will still be able to go back to its original position, same way it was here before. And there is a point at which you will extend this spring, and this spring will not be able to come back to this point it was before. So let's assume that this is the normal position of the spring. On compression, the spring looks like this. On extension, the spring looks like this. So opposite of extension is compression. We want to be careful when you're compressing or extending a body. When you extend the body so much, that body might become so deformed that it will be unable to return back to its original position or the way it was before. And now let's talk about yield point. What is yield point? Well, yield point is simply referring to the minimum stress, in other words, the minimum load that is acting on an elastic material beyond which plastic deformation sets in. It is the minimum stress, the minimum load that is acting on an elastic material beyond which plastic deformation sets in. It means the point at which when a body is extended, that body will not experience what we call plastic deformation. I'll tell you what plastic deformation is in the following set of slides. Now, what do we mean when we talk about elastic limit? First of all, elastic limit simply refers to the maximum load, the maximum force which a body can tolerate, which a body can accommodate, which a body can experience, and this body will still be able to regain its original size. So if you extend a body past its elastic limit, it simply means that that body will forever be deformed, such as the illustration of a rubber band or a piece of cloth that was stretched such that it became torn and became weak. That body has been deformed. So the elastic limit is the maximum force you can apply to a body, and that body will still be able to go back to its original size. If you extend the body or apply a force or a load on the body, and that body is not able to go back to its original position, we say that the elastic limit of that body has been exceeded. We say that the elastic limit of that body has been exceeded due to its inability to go back to its original position. At this point, let's talk about tensile stress and tensile strain. When we talk about tensile stress, what exactly do we mean? Tensile stress simply refers to the force that is acting on a unit area of a wire or on a rod, or we can say it is the force per unit area of a wire or rod. Tensile stress is given by the formula force over area. Remember vividly that force over area is also the formula for pressure, which is measured in Pascal. So it has basically the same dimension for tensile stress. It means the same thing. Stress and pressure are used interchangeably. And what about tensile strain? When we talk about tensile strain, we're simply referring to the extension per unit length. Extension per unit length. Put simply, tensile strain is given as extension over the original length of the material. Extension over the original length of a material. And then we have Young modulus, which kind of brings together the two equations together. It tries to show us the relationship between tensile stress and tensile strain. So when we talk about tensile stress and tensile strain, the ratio of both of them gives us Young modulus. So Young modulus can be defined as the ratio of tensile stress to tensile strain. So stress over strain gives us Young modulus, which is actually measured using the symbol gamma. Stress over strain is what gives us our Young modulus. At this point, let's talk about the energy that is stored in an elastic material. Energy stored in an elastic material. Let's start with the force in a bar. We can call a bar a piece of rod. Now when this bar is heated and then this bar is prevented from contracting as it cools, there is a considerable amount of force that is exerted at the end of the bar. A considerable amount of force is exerted at the end of the bar because normally when something is heated, when the substance undergoes heat and it wants to cool, that substance should be allowed to cool. when you try to prevent that substance from contracting and cooling through its own natural processes, you cause deformity, and deformity comes as a result of considerable force being exerted on that body. So when we're given a bar that has a Young modulus of known as E and a cross-sectional area known as A, we have a linear expansivity of alpha, and then we have a decrease in temperature of theta. Then the expression we're going to have for the bar of Young modulus E is going to become E equal to stress over strain. Stress over strain, of course we know that stress is force over area, and then we know that strain is extension over original length. So we can say inadvertently F over A times L over E. We just change the division sign to multiplication sign, and L goes up, E comes down. So we can now have our final formula. When we make E the subject of the formula, we could have FL divided by AE, or when we make F our subject, we can have EA divided by EAE. That is the Young modulus times the cross-sectional area times the extension divided by the original length. So this is the formula for calculating the force in a bar, the relationships therein. What about the energy that is stored in a wire? Note that the application of force on any wire, provided the elasticity limit is not exceeded, is proportional to the extension provided. That is Hooke's law. Hooke's law applies when elastic limit has not been exceeded. So consequently, the force in the wire has increased from 0 to F. The force in the wire has been increased from 0 to F. Alright, so let's talk about now about the energy stored per unit volume. Energy stored per unit volume is given by WV equal to half times stress times strain. So please do take note of these equations and use them effectively. You know what this implies? This implies that the energy stored per unit volume is given as Young modulus times extension squared divided by 2L squared, 2 times the original length squared. The reason for this is because substances lengthen considerably, and remember previously we talked about something like plastic deformation. Substances lengthen considerably when they are heated or when they are prevented from contracting as they cool. So at this point, we want to talk about what plastic deformation means. So substances which lengthen considerably and undergo plastic deformation until they break down are known as ductile substances. When we heat these substances and they lengthen considerably and they are plastically deformed such that they are unable to go back to their previous state, they are known as ductile substances. On the other hand, there are substances that will break immediately after the elastic limit has been reached. These substances are known as brittle substances. They don't get deformed, they just break immediately after their elastic limit has been reached. Take example, glass. At any point in time you try to extend glass either by heating it or pouring water into it, it will break instantly. Examples are mentioned glass already, and then we also have high carbon steel. However, there are some substances that do not have yield points. They are things like bronze, brass, and many other alloys. An alloy is a combination of two metals mixed together in definitive proportions. So some of these materials, even when you increase their length beyond their elastic limit, they will not go even into plastic deformation. They will not go through the plastic deformation stage. And that is it for today's lesson. Thank you for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear on your screen.